Hello and welcome to the 2020 Southern Illinois University Edwardsville Senior Design Presentations. Our project is called Project Speedtail, and we built an electric longboard. Before we begin, I want to take a moment so everyone involved can introduce themselves.
I'm William Lascala, a computer engineer.
My name is Tayton Rowe. I'm an electrical engineer, and I'm working on the battery configuration, hardware, and motor model of Project Speedtail.
I'm Brandon Myers, computer engineer.
My name is Matthew Dobbs, and I'm an electrical engineering student here at SIUE. Tayton is going to go ahead and kick things off and go over some of the construction of our longboard.
Starting with the hardware, Project Speedtail is built with a stylish 8-ply pintail deck. It has a wheelbase of 38.5 inches. This works better for our application by providing more room for our electronics tray. Project Speedtail's pintail deck has a flat bottom instead of a rounded bottom, which provides an easier mount for the electronics tray. Project Speedtail uses 217mm torque board trucks. These trucks will provide a greater stability and balance for the rider. Project Speedtail needs high-speed, efficient bearings to lower rolling resistance. This will help maximize the board's range and efficiency. Project Speedtail chose to use Bones Red's bearings. They can be purchased on Amazon for a low cost of approximately $18. Bones Reds are one of the most superior bearings on the market today and are recommended and used by many professional boarders. They are superior to many others on the market and are quite affordable. Project Speedtail is constructed with 110mm torque board wheels. Bigger wheels accelerate slower and have a higher top speed and roll over cracks and debris much easier than small wheels. Bigger wheels also provide much more greater ground clearance. Smaller wheels fit on more setups but provide a slower top speed.
Project Speedtail requires an electronic speed controller to power our motors. An electronic speed controller, or ESC, is an electrical circuit that controls and regulates the speed of an electric motor, and in our case also provides reversing of the motor and dynamic braking. Project Speedtail uses two Alien Power System 6384S motors, which both require an electronic speed controller to control. To avoid buying two electronic speed controllers, we used a Flipsky Dual 6.6. This electronic speed controller is two speed controllers built onto one single PCB, which will take a lot less space on our electronics tray, saving room for batteries and wiring. This ESC also comes with a built-in 2.4 gigahertz receiver, which makes it a lot easier to find a remote. We chose to use a Flipsky VESC2 remote control because it has the 2.4 gigahertz capability, but it also has a color LCD screen, making it easier to read. It also has three acceleration modes, low, medium, and high, and a built-in speedometer. After receiving our Flipsky ESC, we discovered that the master side of the board had faulty firmware. Thanks to the indication LEDs, we could see that one of the two green LEDs, which indicates that the ESC is ready and programmed properly, was not on. After contacting Flipsky and working them over the course of 2 months, we discovered 1 week before the end of the semester that the only way to fix it was to use an STV2 link firmware uploader to re-upload the firmware that should have been on it from the factory. Flipsky sent us detailed instructions on how to connect the ESC and the STV2 uploader, but we encountered problems when we attempted to connect it. The STV2 did not recognize that it was connected to our ESC. Between the slow emails and phone calls back and forth with Flipsky in China, we found ourselves in the final week of the semester working on the ESC and no real way to repair it. Our conclusion is that the ESC came with faulty firmware or came broken on the master side. Due to the master side being broken or faulty, we have no way of connecting it to our remote, which is located on the master side, and that is how we would prove that it is functional. The slave side of the PCB functions normally, and that allows us to show motor detection software that you will see later in the video.
Project Speedtail uses two Alien Power Systems 6384S motors. Each motor produces 4,000 watts or 5.36 horsepower. These motors are attached to the board using a Jont's belt drive motor mount system. This system uses 15mm wide belts that wrap around the 16-tooth motor pulley and the 36-tooth wheel pulley. The system mounts the motors behind the rear wheels to allow more room for electronics tray under the middle of the board. Each motor makes 4.5 Newton-meters of torque, which will propel the longboard uphill gradients up to 20% with ease. The electronic speed controller must be programmed to work with these motors, and we have the VESC Tool programming software to achieve this. Hello and welcome to the free VESC Tool from VESCproject.com. This software is purpose-built to configure VESCs, upload firmware, and generate real-time data for electric vehicles. It's currently the leading programmer for electric skateboards worldwide. The simplest way to understand how it works is to walk you through step by step and show the motor detection software in action. So as we have mentioned previously, we found that our electronic speed controller was malfunctioning on the master side. After countless emails and months gone by of attempting to upload the correct firmware to it and working with the manufacturer, we found ourselves with a 50% running electric skateboard. What you're seeing now is what happens when an electronic speed controller has faulty firmware installed. The VESC tool needs to connect to the PCB to allow any sort of programming to happen, or in our case, motor detection. Since the board does not have its most basic firmware installed, the ability to connect to Windows is gone. We cannot run motor detection, we cannot connect to wireless remote, and we cannot scan the port to even see what's wrong with it. The good news is this is a dual VESC, so we have two, one on the left, one on the right-hand side of the board. We have one to power each of our motors, which means that we still have a motor that will work, and we still have a VESC that will work, and we can still run the detection to show you exactly how it works. So we're using Alien Power Systems 6384 motors that produce 4,000 watts or 5.36 horsepower each. These are classified as a medium outrunner, and therefore we have to choose that parameter in the VESC tool. It's important to choose the right one for a lot of reasons, but the biggest is it can cause damage to the motor or the VESC if you pick something that's too big. Moving on to the second parameter, Project Speedtail uses a 12S 5P battery with 6 amp hour Samsung Q30 cells. This parameter tells the software to look for a voltage between 43.2 volts and 50.4 volts, also known as the 12S battery. If the voltage is not found, the program will not run the motor detection for risk of damaging the batteries, motors, or both. Project Speedtail uses a belt drive system as well. We have a 16-tooth motor pulley and a 36-tooth wheel pulley. The diameter of our wheels comes in at 110 millimeters, which is a little bit over 4.3 inches. And after all of those parameters have been set, it's finally time to let the software go to work and find our motor specifications. As you can see, because we're going to be running the VESC on the slave side of the PCB, one of the motors will not be spinning. But what you're going to hear is the software tick through everything and find all of the motor specifications that we would need later down the road to find our motor model, our graphs, and all the stuff needed for the senior design project. So as you can see, after the motor detection is complete, there is an option to test the direction of forward and reverse, just in case you've wired the brushless motors incorrectly. You can easily see right now that the right-hand side of the project is not spinning. It's just the same in the motor detection process that you saw previously. But with the correct firmware on the master side of the PCB, we are confident that Project Speedtail would be writable. Thanks to many of the group members living so close to campus and accepting jobs that are all in the local area, we plan to continue to work with this electronic speed controller and the rest of the project in general to finally get it writable post-graduation, and hopefully you can see it on the street when it begins.
There are many options for onboard battery packs on the electric skateboard market today. Lithium-ion and LiPo batteries are the most common batteries found on electric boards. Many existing boards on the market use 6S to 10S battery packs. However, we chose to use a 12S 5P battery configuration because of the high discharge current capabilities and the added range over the more traditional 6S to 10S battery pack. These configurations will provide a shorter range and lower top speed compared to Project Speedtail's 12S 5P configuration. The 12S 5P battery pack is quite large for a skateboard, but adding more cells adds range and increases top speed compared to smaller battery pack configurations. Our battery pack is 28.5 by 4.5 by 3 inches and weighs 10 pounds. A 10S battery will have an unloaded theoretical top speed of 28.6 miles per hour and a range of 20 miles, whereas Project Speedtail will have an unloaded theoretical top speed of 33.14 miles per hour and a range of 27 miles. A 12S 5P battery pack uses 5 cells per pack in parallel and a total of 12 packs in series. We chose to use the Samsung Q30 cells, which are 18650 milliamp hour lithium-ion cells. They are inexpensive in price and has suitable performance. At their nominal voltage, 3.7 volts per cell, Q30 cells discharge at 15 amps continuously, meaning that our 12S battery pack can discharge 75 amps continuous or 100 amps peak. Thanks to 2 amp 12S charger, our 12S 5P battery pack will charge from low voltage cutoff of 33 volts to a fully charged 50.4 volts in just 6 hours. Traditional battery packs use pure nickel strips to attach each cell in the battery pack. However, Project Speedtail chose to use Vrusen battery building kit. This kit snaps together just like Legos and simplifies the 18650 battery building process. The kit has the added benefit of spacing the cells just far enough apart that an air gap between the cells aids in cooling the entire pack. The operational range of 18650 cells are 2.6 volts to 4.2 volts and can be very dangerous when overcharged and over-discharged. The lithium-ion cells are known for getting too hot and causing fires if used incorrectly. To protect these cells from damage, Project Speedtail has used an HDX D596 Bestech 80 amp max discharge battery management system. The battery management system, or BMS, has 2 main operations. First, a battery management system manages max discharge and short circuit protection. Second, a BMS manages the cells. When a battery pack is discharged and recharged repeatedly or cycled, the cells can become skewed at full charge. A battery management system not only protects the cells, but also manages them from operating outside of their safe operating range.
Moving forward to the engineering specifications and test plan. As we've said previously, the electronic speed controller has either a bad master side or faulty firmware installed. Because of this, we cannot ride it to physically test in the real world a lot of the things that we wanted it to be able to do. One of those things is top speed. We wanted Project Speedtail to be able to go 25 miles an hour, but if you reference the motor model, you'll notice that the theoretical top speed under ideal conditions is 38 miles per hour. If we assume 85% efficiency, that means that we're going to be at 33 miles an hour top speed, which is controllable through the electronic speed controller, well above our first requirement. We wanted Project Speedtail to have an effective range of 15 miles. Based upon our motor model, we found that Project Speedtail under ideal conditions would be able to go 21 miles. Assuming 85% efficiency, that puts us at 18 miles, again, above our initial condition. One of the things that we could test was the weight, total weight of the entire board. It came in at 34 pounds, and we wanted to be under 40 pounds at the absolute max. We also could test the absolute max rider weight. With a 250-pound rider, we wanted everything to work just as it should. And of course, we can't go out on the road and actually go over the bumps and everything that you would, feel if you're riding it down a sidewalk. But standing on it with a weighted backpack shows that it can handle a rider of that weight. We wanted Project Speedtail to be able to climb hills with a 20% gradient. Using the motor model, we found that the torque should be more than enough of an average weight rider, assuming 185 pounds, to bring them right up that hill.
Moving forward to the existing market, as you can see here, we have a list of some of the different boards that we tried to compete against. The biggest one that we tried to compete against was the boosted boards. Looking at the boosted board, the biggest one that we looked at to try to compete with was the boosted Stealth. Here you can see that they have a top speed of 24 miles an hour with a range of about 14 miles. As you can see, the boosted Stealth has a price of about $1,600. In comparison with our product, we are under that by just about $100 to $150. As discussed before, the top speed was set to 25 miles per hour in the speed controller for rider safety, but would have a theoretical top speed of 33 miles per hour. making our board both faster and cheaper than our target model on the market.
And that just about wraps up Project Speedtail. Although it wasn't 100% successful, we did manage to accomplish a lot of interesting things on this, and we all feel that we have learned a lot. Thank you all for taking the time to watch this presentation, and given these uncertain times, from everyone here at Project Speedtail, we hope that you all stay healthy and have a wonderful day.